We're just going to restart it. Welcome back. This is part 2. Okay, neutralization reactions in salts. What happens if you combine an acid and a base?
Neutral.
See, physical science falls for it and they go, a bomb. No, you get neutralization. Okay, so you get a salt. It might not be table salt, but you get a salt and water. So here we've got an acid, a base. See that OH? HOH. Is that an acid or a base? It's both. And what's HOH more commonly known as? Which is water. Water.
I thought water was neutral.
It is. But notice water is made out of an acid and a base. And that's why it's neutral.
Wait, hold on, wait.
Water is both.
Hydrogen's an acid?
If it starts with hydrogen, it's an acid. If it ends in OH, it's a base. So water is the both. Okay, and NaCl is salt. So there's my dude chilling on the beach. Okay. All right, you get another new concept. Yay! Redox reactions. Now you might have touched on them in honors, but we're going to go deep. Okay? A salt is any compound whose cation comes from a base. So here we're looking at that same reaction as a net ionic equation. So there's your hydrochloric acid, there's your sodium hydroxide, there's the water, and there's the salt. And we can mark out things that are on both sides. Sodium is on both sides, chlorine is on both sides, and look what's left. Hydrogen plus hydroxide, hydrogen ion yields water. Very satisfying. Okay, so redox reactions, as the cool kids call them, or oxidation reduction reactions, transfer electrons. They don't transfer atoms, they transfer electrons. Okay? So how we know what's going on here is this little mnemonic device, another one I didn't make up, called Leo the Lion Says Grr. So there's Leo, and what's he saying? Grr. Okay? So, and I'll tell you what that means example. So this is a really important part of chemistry for everyday life. Things like corrosion, rusting, silver tarnishing. Also electroplating, like electroplated jewelry or silverware. Also batteries. Batteries are super important. Electric cars and things like that, right? Okay, all very practical. Okay, so this is part of chemistry that we've known about longer than chemistry. People have been concerned about rust since the Iron Age, thousands of years ago. And what causes rust? Redox chemistry. So there's part of this that's confusing as a result. But if you remember Leo, you'll be okay. Okay, so oxidation. When an atom, ion, or molecule becomes more positively charged, we say that it has been oxidized. So how does an atom become more positively charged? What is it? Does it gain or lose electrons? It loses electrons, okay? So the loss of electrons is oxidation. The loss of electrons is oxidation, Leo. The loss of electrons is oxidation, Leo. Got it? The loss of electrons is oxidation. If things are becoming more positive, they're losing electrons. The loss of electrons is oxidation. Okay? So now, this is where it gets a little iffy, but you can do it. Okay? When an atom, ion, or molecule becomes more negatively charged, so how does it become more negatively charged? It gains electrons, right? Then we say it has been reduced. So the gain of electrons equals reduction. And that's all confusing, because if I gain fat, I am not on a reduction diet, am I? But I am not an atom gaining and losing electrons either. So just remember, the gain of electrons, GER, is reduction. This has been around longer than chemistry. We have been concerned about rust. Okay, so now, everybody cool so far? Okay, so now let's talk about it. So here I have a reaction, okay? And calcium is just an atom, and it's neutral. I'm going to put a little no symbol through it. It doesn't have a charge. Oxygen is just an atom, and so it's neutral. No charge. But over here, I have an ionic compound, calcium oxide. What charge are the calcium ions here? +2, because over here, +2, right? So this one is +2. And what charge is oxygen? -2, okay? So calcium is +2. Oxygen is -2. Everybody good so far? So now let's see what's happening. Calcium is going from neutral to +2. Did it gain or lose electrons? It lost, because it was neutral and now it's positive. It lost 2 electrons. So it lost electrons, so was it oxidized or reduced? The loss of electrons is oxidation. It was oxidized. Isn't it fun learning something new? Okay, now oxygen. It went from neutral to -2. Did it gain or lose electrons? So was it oxidized or reduced? Reduced. Y'all are so smart. Y'all did great. Kind of understanding that a little bit. All right. There's another new thing for you to learn. It's very exciting. Okay. So oxidation numbers. Remember how I told you that charges have to be balanced too? Okay. And remember when in honors you learned 1, 2, 3 skip, -3, -2, -1 zip, and I told you there's more to it that you would learn one day? Today is that day. Today you get to learn what more to it there is. Okay, so we are going to learn how to assign oxidation numbers, and it's a way to keep up with the electrons in the compound that must be conserved because of the law of conservation. And all it is a list of rules you apply. Okay, rule number 1. I'm going to go over them quickly and then I'll show you how to apply. Atoms in their element form are 0. So H2 is an element, they're both 0. Monatomic ions. So it's just one atom, then you use the oxidation number equivalence equals their ionic charge. So if they become an ion, they're 1, 2, 3 skip, -3, -2, -1 zip. Non-metals, over there by the fire ant, usually have negative oxidation numbers, and that's why there's a fire ant there, because fire ants are very negative, right? But there are some exceptions or some applications. First of all, oxygen is usually -2 because of 1, 2, 3 skip, -3, -2, -1 zip. However, when it's in a peroxide like H2O2, then each oxygen is only -1. Okay? Which you might have thought about that before. You might have thought before that that doesn't add up according to what I know. Okay? Hydrogen is usually +1 when it's bonded to nonmetals. So whenever it's acting like everybody else in its family, it's a cation sitting over there by the kitty cats, right? All positive. But remember on our AP test, there was that tricky problem where it wasn't, instead, it was -1. Remember that? And y'all all figured it out pretty good. So when it's bonded to a metal, then it's acting like an anion. It's acting like it's from the other side of the periodic table. Then it's going to be -1. I've seen periodic tables that have hydrogen in the middle floating above all the other elements like the king element, because it doesn't quite fit over there. A lot of times it acts like it's on the other side of the periodic table. So sometimes if you ever see it, that's why it's king element, because it can do either one. Okay, and you just have to look at what it's bound to. Okay, fluorine is -1 in all compounds. Well, good. I'm glad somebody's sticking to the number I learned. Other halogens are -1 in most binary compounds, but when combined with oxygen, they're positive. Okay, it'll make more sense as we do it. The sum of the oxidation numbers of all the atoms is 0. Whew, at least the math is going to be easy. The sum of the oxidation numbers in polyatomic ions is equal to its charge. It'll make more sense when I show it to you. Okay, let's do some of them. Example, what is the oxidation number of sulfur in each of these compounds? Well, here's H2S. So H2 is +1 because it is it's a cation, it's first. It's bonded to a nonmetal, and the whole thing has to be 0. I have 2 of them. 2 times 1 is 2. My whole math has to equal 0. What does X equal? -2. Were you going to tell me the answer or have a question?
I had a question.
What?
If fluorine and oxygen are both always negative, they never bond.
I would be careful of saying never. I'd need to find out more about that. Because I know chemistry nowadays make things bond that don't in nature. They do things to them and make things bond. So I'm not sure. We should find out. Could be, could not be. Okay, so y'all all said that X has to be -2. Everybody understand that? Okay, here it's just an element, so what does X equal? That's right, nothing. Good job. Everybody knew that. Nobody said anything but nothing. Well done. Okay, elemental is 0. Here is binary, and it's bound to chlorine. Chlorine, when it's binary, is -1. So go on to the next page. So we've got X plus 2 times -1 equals 0. What does X have to equal? +2. Y'all are doing great. Y'all are brilliant. Okay, sodium sulfate. Sodium is +1 from 1, 2, 3 skip. -2, -3, -1 zip. Oxygen is -2. So we've got 3 of them. Sodium is 1, and we've got 2 of them. So we got 2 times 1 is 2, plus -3 times 2 is 6. What is 2 minus 6? -4, but we need it to be positive. We need it to be positive, so it equals 0. Did y'all just follow what I did? It was kind of backwards the way I did it. Think about it this way. What do we add to 2 that when we take away 6, we get 0? What do we add to 2 that when we take away 6, we get 0? Yes, +4. Good job. When in doubt, solve it on your calculator. Unless it's in the non-calculator part of the AP test. Okay, here, this one is polyatomic. It's an ion. Do you see how it's -2? So this time the answer is not 0, it's -2. That was that last part right there. So oxygen is -2, and I have 4 of them. So what do I add to -8 to get -2? 6. I hear those little 6s out there. Good job. Well done. All right, how are we feeling about that? Not terrible? Okay, next idea. Oxidation of metals by acids and salts are signal replacement reactions. They're also called displacement reactions. So for example, I got magnesium and hydrochloric acid, and the magnesium cuts in and displaces the hydrogen. So if we look at the oxidation numbers, the oxidation number of magnesium is 0 because it's just an element, it's elemental. And the oxidation number of hydrogen is 0 because it's elemental. Hydrogen is +1 because it's acting like a cation. Chlorine is -1 because it's following those rules. Okay, and over here, I've got magnesium, which is +2, because of now it's being an ion, and that's 1, 2, 3 skip, -3, -2, -1 zip. And chlorine is -1 for that same reason, right? So now we want to look at what's going on. So my magnesium is going from 0 to +2. So did it gain or lose electrons? It lost. So was it oxidized or reduced? So smart. Y'all are doing great with this. Okay, hydrogen goes from +1 to 0. Did it gain or lose electrons? It gained 1, right? Okay, so was it oxidized or reduced? Reduced. Isn't that fun? You're learning college level chemistry here. And chlorine does nothing, it is a spectator. Spectator ion. I think it's fun learning college level chemistry. I think it's fun teaching college level chemistry in high school. Okay, so the net ionic equation is magnesium plus the hydrogen ions makes the magnesium ion plus hydrogen gas. There's the metal for acids reacting with metal. See my metal guitar? All right, the activity series tells if one of these reactions will happen or not. Think of it like a strength ranking. The strongest element on top, the weakest. So everybody look at the back side of the green page I gave you and tell me, can gold replace copper and copper chloride? No. Gold is a wimp. It can't replace anybody. That's why it's unreactive and found uncombined, and you might find a gold nugget one day and strike it rich. Do you know that Paulding County used to be called Indian Gold Territory? You can find some gold here. You could go to the Gold Museum in Villarica and learn all about it. Okay, can aluminum? Yes, aluminum can do it. Okay, concentration of solutions. Concentration tells you how much solute is dissolved in a solvent. The symbol is square brackets. Molarity tells you the number of moles of solute dissolved in a liter of solution. It's a definition that I think might be on your AP fact sheet I gave you. Somebody should check it and find out. If not, you need to memorize it. Molarity is moles of solute divided by liters of solution. If something is 1 molar, it has 1 mole of solute in 1 liter of solution. The abbreviation for solution is that. Okay, good so far? Okay, so for example, what is the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to make 125 milliliters of solution? Okay, so how do we do this problem? If we have grams, what always needs to go with graham crackers? M&M's. So we know we're going to need the molar mass. It's 142.1 grams per mole. Okay, now we're ready to do the problem. We start with what we know, and what we know is 23.4 grams divided by per 125 milliliters of solution. Good? Okay, so let's get rid of these grams first. What goes in the denominator? Grams. And we want to change them to moles. See what's in the numerator? Moles. How do we get from grams to moles? Molar mass, 142.1 grams per 1 mole. Grams cancel out. And now I've got moles per milliliters. Is that what I'm supposed to have? No. I'm supposed to have moles per liter. What's the relationship between milliliters and liters? That's right, 1,000 milliliters in 1 liter. Milliliters cancel out. I've got moles per liter. That's the right units for molarity. 1.32 big M. We could put square brackets around it, but I put a box around it. Welcome.
I left my water bottle in here.
Oh, you should get it, especially if it's one of those expensive Stanley cups everybody's so crazy about.
No.
Okay, expressing the concentration of electrolyte. When an electrolyte dissolves in water, the ions are free floating in the water, the little swimmers. We can think of their amounts in moles. Oops. My sleeve gets electrical and it messes it up. For example, 1 mole of sodium sulfate becomes 2 moles of sodium ions and 1 mole of sulfate ions. So this is how I explained it to the other class. Remember, moles is a number like a dozen. So imagine I have made 12 little Lego figurines out of 1 big red brick, and I stuck 2 little green bricks on it, okay? I'm making a water molecule with 1 big red oxygen brick and 2 little green hydrogen bricks on it. So now I have 12 little figures, right? But now I've decided I want to build something else. So I break up all of my Lego figures. I still have 12 red ones, but how many green ones do I have? 24. Do you see that? That's what this is. That's our little Lego, and it's got 2 sodiums for every 1 sulfate. 2 moles of sodium for every 1 mole of sulfate. Can you imagine that? Good. Legos to the rescue. Enter converting molarity, moles, and volume. Okay? If we know any 2 variables in the molarity equation, we can calculate the third. Yay, math. For example, how many grams of sodium sulfate are needed to make 0.350 liters of 0.5 molarity solution? So our formula is molarity equals moles over liters, right? Okay? So our molarity is that. 0.5, we're substituting it in. We don't know the moles, so moles is our X. Over our volume, 0.35 liters. I didn't put all the extra zeros down. So I can solve that. Multiply here to get out of the denominator, multiply over here. That equals 0.175 moles. Yay, now I have moles. I wasn't asked for moles, I was asked for grams. So what am I gonna need? What goes with graham crackers? M&Ms. We need molar mass. Luckily, it's the same molar mass we had before. That was nice of them, 142.1 grams per mole off the periodic table. So now we can do our math. We're gonna turn these moles into grams. 0.175 moles. Use my conversion here. 1 mole goes in the bottom. 142.1 grams go on top. And I get 24.9 grams. Put a box around it. That's not terrible, is it? Okay, last idea. Not last, next to the last. Dilution. Making solutions less concentrated by adding water. Notice adding water does not get rid of any of the moles of solute in the solution. It's based on the idea that molarity is moles per liter, and what you do is you use the molarity and the volume of the concentrated to calculate the molarity and the volume of the diluted, because moles in the concentrated solution equals moles in the dilute solution. So here's my concentrated Coke, and there it is dilute, because it's been sitting there in that ice for a little while. Do y'all prefer it concentrated or dilute? I prefer it dilute. Coke over ice is way better than Coke out of the bottle. No? No. I'm being disagreed with. Okay, for example, we're going to figure this out. We want to make a 250 milliliter 0.1 molar solution from a 1 molar stock solution of copper sulfate. Okay, so my concentrate is, the molarity is 1, and I don't know how much concentrate I need, so that's my X, because I need to find out how much I need. But the molarity I want when it's all done is 0.1, and the volume I want when it's done is 250 milliliters. And it doesn't matter that this is milliliters, because this, remember on the gas laws, it didn't matter if we were setting up something with the equal, as long as our units are the same on both sides, we didn't have to worry about it. We just had to convert Celsius to Kelvin, remember all that? If not, that's okay. Just know it doesn't matter that it's in milliliters. Okay, so we're going to solve for X. X equals 25 milliliters of concentrated. So what I would do in my volumetric flask, here's my little flask. There's my flask. It's sort of a terrible looking flask. But anyway, there's my flask. I'm going to pour that in, and then I add water up to the line to 125. And I will have this new dilute in the right amount. I pour in 25 mils, then I fill it up with water to the line until I've got 125. So that's easy math, isn't it? Okay, now yeah, we got time. Last point, yay! Solutions, stoichiometry, and chemical analysis. Because moles of solute equals M times V, we can use that to get mass in stoichiometry. Example, how many grams of calcium hydroxide are needed to reduce 25 milliliters of a 1 molar solution of nitric acid, HNO3? Okay, so our moles equals times the volume. So this is our formula right there. And we are going to start with our, I'm going to switch them. I'm going to write volume first, just because I like the way it looks better. But don't let it confuse you, because remember that rule in math, A times B equals B times A? Is that the commutative property of multiplication? I think so. So we're going to use the commutative property. I'm just going to switch these because I like the way it looks better. So I'm going to do 0.0250 liters. So this time I did change it to liters. So I did 3 frog hops, whoop, 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 more fun with sound effects. So change that to liters. Okay, King Henry's daughter. Okay, and now I'm going to multiply it times my M, which is my thing here is that, I think I did a typo here. Let me double check it. Yes, this is supposed to be 0.1. So move your decimal point there, just because I did a typo right in the problem, and all my work goes with that. And if it was just 1, it'd be boring. So I don't want it to be 1, I want it to be something else. So I'm going to multiply this times 0.1 over 1 liter. Because now I've got moles over liters. Okay? So I changed it to liters and all that. Okay, times 100. Okay, so this equals 2.5 times 10 to the negative 3rd power moles of HNO3. Okay, and now I'm going to write my equation. So I've got 2 HNO3 plus calcium hydroxide, CaOH2. Oops, the parentheses goes right there. I almost wrote it in the wrong place. Yields 2H2O, because it is an acid and a base, makes salt and water, plus, and this is my salt, CaNO3 taken twice. Okay, there's my formula. Okay, and now we're going to get how much grams of calcium hydroxide just doing a stoichiometry problem. So my ratio is 2 to 1, because of that 2. The other one is 1. My calcium hydroxide, that's what I'm going for. So I start with what I know, what I got here. It's 2.5 times 10 to the negative third power moles of this HNO3. Okay. Moles go on the bottom, so that's my 2 right here. 1 on top, so 2 moles of HNO3. 1 mole of my calcium hydroxide. This time I'll put that in the right place. These are moles. Okay, now moles go down here of calcium hydroxide, and to get it to grams, we're going to look. What goes with the graham crackers? Molar mass. And its molar mass is 74.1 grams. So 74.1. These cancel out, those cancel out, and I'm left with 0.0926 grams of calcium hydroxide. So we'll practice that, it'll get easier. Okay, last little idea. Chemists often carry out titrations to find out unknown concentrations a standard solution with known concentration is added to a solution with an unknown concentration until it reacts completely. This is called the equivalence points. How you know it's reacted completely is with an indicator. So let me explain it to you in real words. And we'll do this in a lab. Okay, so how it works is, remember the burette? I know y'all used it in Miss Corn's class. Y'all remember burette? It's the thing with the stopcock, remember that? You turn it and let the liquid out, and then you turn it again, and you can measure how much you let out. Okay, so what it usually is that your unknown concentration is an acid in a beaker. You put a base with a known concentration in the burette, and you put phenolphthalein in it, usually, an indicator in the acid. The acid stays clear, it has no color, until you let it out until it starts turning pink. And then you do it 1 drop at a time, swishing after each one. And when you put a drop in and you swish it and it stays pink, you have reached the equivalence point. And you have neutralized your it to where it was neutralized, and then you add 1 more and it became base, and the phenolphthalein was pink. And so that's a titration. College chemistry lab teachers love them. You'll have to do them in college, and we'll do one here. So can you sort of imagine that? And they can be very frustrating if you don't do your math first, so you don't know what it's going to be close to, probably. Because if you're going like 1 drop, 1 drop, 1 drop, and then, or if you go too fast, and you go too fast, and boom, it's hot pink. And you pass the equivalence point too fast. So what you need to do is kind of drop down to it sort of quickly and then go slow. But it can be very frustrating, just to let you know, or fun, because it's hot pink, and that's kind of fun. All right, so that's it for this unit. We'll start working on it tomorrow. Science is great. Like, share, subscribe. Yay!